Welcome everyone to IC43, the effect of whole body vibrations on tissue loads. I am Patricia Karg, and I'll be moderating today's session. And as you've seen in other sessions, please remain muted during the presentation. Please put comments and questions in the chat as they arise. And Dr. Alexander Siefert, who's your presenter for the session, will address the questions in the end. And I will also, at the end, announce the CEU code as well as put it into the chat. So with that, I'll hand it over to Dr. Alexander Siefert.
Okay, thank you, Patricia, for the nice introduction. As you already mentioned, the title of my talk today is The Effect of Whole Body Vibrations on Tissue Loads. First of all, a short introduction of myself. My name is Alexander Siefert. I'm living in the northern part of Bavaria in Germany. So for me, it's afternoon. For you, it's hello, good morning. I'm the managing director of Symposium and a shareholder of Symposium. I have about 20 years of experience in finite element analysis, especially in the field of seating comfort analysis. I'm the developer of the virtual human Joe model, which we will see later. And here's the contact data. And there is nothing I have to disclose before starting the presentation. So let's start with a first overview about the content of the presentation. So first of all, I give a general introduction, not specifically for wheelchair users, about state of the art of whole body vibrations. What is it and how is it handled in other situations, other industries? Then something about wheelchair users, studies which have been carried out and published about daily vibrations, what is the level of the vibrations. Then I will go over to finite element analysis to give an introduction to that, and then telling something about the virtual human Joe and why you can use that for this kind of analysis. And finally, I will come to the pilot study, covering some scenarios which are initially defined in the published setups of the studies and showing some typical vibrational loads for wheelchair users. And at the end, a quick summary and outlook. Okay, let's start. So first of all, state of the art of whole body vibrations. Some general information, what is it and why is it necessary to look on that? And what are the setups in other industries? Okay, whole body vibrations occur in our daily life. In all situations we have. In the traffic, when you're sitting in the car, you feel that, okay, it's a bumpy road or it's a smooth road. At working places, not all environments, not in the home office, but maybe if you're on working construction sites, you have that. And we know that from sport activities. And it is very important when you look on this kind of setups and how to analyze whole body vibrations, you have to cover all parts which are including that. So here's a small video showing Joe going over virtual setup. And by that, you can easily describe what is the complete system which has to be accounted when you do the evaluation of whole body vibrations? Because here we can see all the parts of the whole system, which is first the surface profile of the road. Is it bumpy or is it not bumpy? Have we cobblestones or is it plain concrete? Then on top, the tire setup. Are we using, which kind of tires we are using? Next setup, the frame. Is there suspension included? How is the cushion supported? And obviously, how is the cushion itself has the possibility, the capabilities to reduce the vibrations which are induced via the road and the frame. And finally, what is very important, if you do this kind of analysis, you have to include the human, because our human has also a dynamic behavior. And you cannot just put the rigid block on it. You have just to put the human to get the right level of the setup. And when we later on maybe a little bit discuss, okay, what we can do to reduce this for our customers, for our patients, we can focus on different setups. Obviously, we will see in the second chapter, there are some standards defining what is a good profile for surfaces to reduce the vibrations which are induced by the pathway, for example, or the pavement. But the main part, what we can do or the manufacturers can do, okay, they can define the right tires, the right frame, and the right cushion. Because We have obviously different kind of humans, different kind of customers, different kind of patients, but they cannot be changed. The main part where we can influence the reduction of the tissue loads and the vibrations which are induced to our customers is the three parts we see here in red setup. So this topic, when I looked, I would say I'm in the field of wheelchair users at ISS or ESS or other conferences. I would say I in this field about 10 years. And when I look on the exhibition stage, I have seen there are some comments about vibrations, but not too much. When we look on other industries, especially where we recognize higher intensities or long exposures of vibrations, then this is a very hard criteria for products. As we can see it here for a forklift driver, you can see he's going over, I would say more or less, typically a pathway which is normal for companies. And you can see how much shaking he has sitting on that forklifter. And based on that, and many studies started, I would say, in the 80s, 70s, 80s, 90s, it's known that there are negative aspects, not only comfort, but also on the health. And especially, for example, here in Germany, based on some studies, we have recognized that forklifters, digger drivers, they have some disease for especially the lumbar spine, the lower part of the lumbar spine, some degeneration. And we have here in Germany official occupational disease, BK2110, where you just say, okay, if this is the case coming from your working environment, you get some money from the insurance company. I'm not really sure what's the state in the US or other countries, but that's here, and I think that's the same for you too. So, and based on that, the EU, for example, has introduced some standards. In 2002, they introduced standard 2002-44 EC, and this is defining a procedure how you have to evaluate a working environment to make sure that your employees are covered by these negative aspects on their health coming from these vibrations. And obviously all the manufacturers have to do that because they are selling these products and they're saying, okay, I have to fulfill that. So what is typically done in this procedure evaluating vibrations? Here we see a setup of a forklifter, and you can see they measure the vibrations on top of the seat surface with a seat pan. A seat pan has a diameter of 200 mm. It's a rubber-like material, and in the center of it, we have a small acceleration transducer, which is just located here where we have the coordinate system. And it's measuring on the specific area of the working environments, the setup where we have vibrations. And this is a little bit converted. It's just post-processed this acceleration data, some filters on top, but this doesn't matter. So you have the right value of the vibrations at your working site. And then you have to combine that. How much time in a working hour of 8 hours I have this exposure? How much time my employee has this kind of level of vibration over the whole working day? And if you have these two combinations, then you can do the setup based on the standard. And there are two limit values. The first one is called exposure action value. It's a value of 0.5 meters per second squared. This means if you're below that, it doesn't matter over the whole day what happens. You don't have to do anything. No limitation about hours in that vibrational environment, doesn't matter. You are fine. If you're above that, then the 8 hours are reduced based on the standard. And the second part is the exposure limit value. It's about 1.15 meter per second squared. And this means if this is occurring, then you directly have to do something against the vibrations, because directly it's known we have negative aspects. So you have on the one side the vibrational level, you have the time of exposure, and based on the standard, you get a plot like this. We see here red part, green part, you are safe, red part, you are not safe. On the lower part, we just see the time of 8 hours. And on the upper part, on the left side, on the y-axis, we see the acceleration measured. So as I mentioned, you can see when I have a value of 0.5, I have a green light up to 8 hours. If I'm above that, I have to reduce my exposure. And this is how it works, how you do it typically in this kind of environment of vibrations. So the question is this somehow useful for us, and how we can convert that information? There have been some studies, and this is where the point I come now to the next chapter about wheelchair users' daily vibrations. So I looked around in the last years, what are studies published by several setups, and I really have to emphasize the most relevant work for me I found there was the work of the University of Pittsburgh. There have been several publications, and I was mainly working for my pilot project. I was working or referring here to a publication of Wolf of 2007. You see the reference on the bottom of that setup. He has investigated with different humans, test persons. He has investigated 9 different pavements, which we see here. It's a poured concrete, what means a plain concrete, and then different where we have just, we would say pavements with different level of joints, what is the spacing in between. And then he investigated these 9 typical setups with 2 kinds of wheelchairs. On the one side, he was using a manual wheelchair, and they just specified a speed of 1 meter per second. And then they have also investigate with the 10 healthy test persons, a power wheelchair setup with first 1 meter per second, and then they increased it to a double speed of 2 meters per second, just to see the influence if you increase that speed. And most probably you already know what's going on when you increase the speed. And here are the results. Just taking into account what I have mentioned before, the acceleration values here, they are called root mean square values. This is a specific post-processing of these time domain signals of the accelerations. And when we look on the different setups and just remember what kind of limit values we have, 0.5 and 1.15, we already see that for the manual chair, the one manual wheelchair with 1 meter per second, that we have different states where we are above the action value. What means when I would follow that and I know, okay, I have 8 hours of them, then I have normally, if this would be a working environment, I have to reduce the hour. And when we look on the power chair, especially from 2 meters per second as a speed, we see all of the pavements are above that. So that means directly you are not allowed to do that 8 hours. Obviously, patients, clients will not do that 8 hours, but you already see, okay, the vibrational daily setup is not really low. We have to take that into account. So, and based on that, to get a correlation, so we see many daily setups are exceeding this action value. Based on that, they have developed a very nice tool, which is called the pathway measurement tool, PassMeT, and you see it here on that setup. And this setup covers 2 points. On the one side, we have we have here the wheels just for the forward movement. You can measure that. Then you have a laser, which is just measuring the distance of the surface of the pavement, just as an indicator for the roughness of that. And then we have also some acceleration meters. So, and based on that, they did the following. They defined somehow a roughness index. A roughness index, which is describing how rough is my pavement. And the goal was for this study was, okay, if I have this pavement and I can somehow correlate that to an acceleration value, then I know which are my limits for my acceleration values. I can also just refer that to my pavement roughness and say, okay, this is a good pavement roughness. And this is what they did, what we see in the next 2 slides. Here just some examples. So the pathway roughness index, the PRI, is the vertical displacement of a wheel when running over a horizontal surface. So what means the wheel is going like this direction, go up and down, and this is just how much millimeters of 1 meter, how much height difference you have. And here we see some examples on different setups. We say, I would say here, standard pavement as we have it everywhere, then more concrete setup, but with some bigger gaps. I would say these are when we see that it's more or less obstacle. We directly can see that the PRI value is increasing from 30.7 up to 60.2.2. And then finally, I would say this was maybe some years ago a pavement like we see it here on the left side. This is, after a while, a pavement is losing the setup, and based on that, you get some higher and higher PRI value, which is here in this case 74.1 millimeters per meter. So just these are typical values, and based on that, they did also at the same time the measurement of the RMS value, which we just used for defining the exposure limit value, for example. And they find out, okay, there's a good correlation between the pathway roughness index and the RMS acceleration value. And based on that, there is a new standard in the US, the STM E3028, where they say, okay, we have to make sure that for a pathway, for a new pavement, we should normally not come above 50 millimeters per meter for new designs. And the idea is behind that is they just defined it like this, and they say, okay, this would allow us, over following the EC standard, the European standard, that you can over this pathway 60 minutes, which is maybe acceptable time over the day. So, but the question I have, if you do that design, what happens over the years? So we have seen the two examples, just going one slide back, on the left side and the right side. I would say after some years, this will change. So what happens after a while? This is, I would say it's fantastic doing that and specifying that, but what happens after years? And further is, we're talking a lot of acceleration values. When we talk to customers, when we do evaluations of cushions, we normally not talk about vibrational values, accelerations. We are talking about pressure. We're talking maybe sometimes, if you are have more sophisticated approach, we're talking about tissue loads, tissue strains, but not talking about vibrational loads. So the question here was, what does this mean, this kind of vibrational load regarding tissue loads? To get also an understanding, okay, is this useful for us? Is this enough information? How is the transformation to our risk evaluation normally based on the setup of pressure injuries? So, and for this, we just carried out this pilot study. And first of all, I will just introduce here now the finite element analysis, our approach to get a more detailed investigation of the setup. And then I will tell you something about our setup of the virtual human show, which we introduced here in this analysis. So finite element analysis, if someone has maybe joined one of my presentations at the last IS or ever has seen a talk of me, you maybe know this setup. Finite element analysis is a standard calculation tool which is used in many industries just for simple or as complex cases as we have here, just to evaluate designs. So in this video, we see first, starting now, starting now, this is a real car crash. And then the second part, this is already virtual. And what is the benefit of virtual? Benefit is here, we can, at every second, we can see how the structure behaves, which column fades, where we have to increase material, where we have reduced material, where we put more stiffness. So the benefit of FEA is we have virtual, we have no hardware. You can imagine for this kind of setup, this is really costly. But hardware means also if you have a new wheelchair design, if you have a new cushion and you want to change that, you not have to produce it. You can just do it virtually, and then you say, okay, if this is fine, then I will produce it. This is a general benefit. Another benefit maybe you are aware of, you have 100% reproducibility. Let's assume I make a simple example. You have a customer and a cushion A and B. You will do a cushion A test before Christmas and cushion B test after Christmas, and then you have differences in the result. This is an example I used many times in the automotive sector because it's easily, we know, okay, we are changing a little bit over Christmas time. And the question is then, when we changed weight, when we have been skiing, when we get more relaxed, so will this influence the results between variant A and variant B of the cushion? Yes, it will. And this is the case, then you have in really hardware setups, if you have test persons in there, you have not a 100% reproducibility. And this is the case here. If I do the analysis always again, I will always get the same result. If I change something in the setup, I will see a difference. So what means I get a direct correlation between change of the setup to the results. And this makes it very easy to see, okay, this is a benefit or is not a benefit. Further, as we can see here, and you will see that hopefully later on and understand it, we can somehow increase our know-how using that kind of virtual tool. And finally, less hardware means reduced time for setting up a new system. And this means obviously reduce the costs. So, and when I look currently on the status, I see, okay, we have many standards which are specified by inventors. Also, I know manufacturers are doing with test setups. And just looking what I described before, which works, which does not work. I will not say that I directly want to exchange real test persons with virtual world, but I will just show some parts where I think if we combine that in a good manner, then we have a benefit for everyone for us. So reproducibility for the ISO standards with the indenter test, yes. For test person's test, this is not a real test person, but this setup, not really, but it's a real case. It's a real case if I have the right person here. This is more or less, I would say, no one of us has a rigid buttock. So this is not really a real scenario. Evaluation quantities. We have pressure maps, yes, but if we have not the right buttock, what we take out as a message of that? It's just an information about how the cushion behaves with a rigid indenter. It's nothing about the interaction between human body and the cushion. And very often we look here on force deflection curves. This is a global value, but sometimes it's more interesting to look on local setups. Digital, not really the case, although this is very simple to do as a digital setup. Time and costs depends. If you are fast in hardware manufacturing, obviously not a lot of time, not a lot of costs. If it takes a while to make a new setup, then you have really some problems about that. Okay, so then I did a small example just this Sunday morning, just to explain a little bit more. Okay, what can we do? And I just did a foam setup, a cubic foam setup, 50 millimeters height, and just put on top the ISO indenter. And I just want to explain you, okay, what could be the benefit? And this was amount of hours for me, 1 hour. I first just did apply the 800 newtons. And then we looked here in the middle, we look pressure map, you say, okay, nothing new. I could also show you a force deflection curve, nothing new, we can do that. But I can there also look on the friction. What means the friction between the indenter and the setup. We have some specific ISO indenters with some specific sensors. This is correct, but we have not a resolution like we have it here. I can do really resolution similar to our pressure map resolution, just showing you the friction. This is very interesting when we look, for example, to the IT region. And another thing I did on sine dive was also left side is the typical foam block. And then I said, okay, let's see what happens if I cut the foams, because there are many setups out there. Doesn't matter if it's an air cell cushion or is it a cutted foam, where we have a change regarding to that. And I just did the same test, first loading vertically, and then I just do a horizontal movement to see what happens to the cushion. And this is a cross section at the sagittal plane. And this is what I say, okay, I can directly look inside how the cushion behaves. On the left side, the typical foam block, it's not really difficult to understand. But on the right side, this is also with, I done that within 1 hour, you directly see, okay, how the blocks behave to each other. And I can easily change that to make the blocks wider, smaller, change the geometry. So a lot of possibilities. And this is what I say, there are manufacturers out have this kind of setups, but I think they have an idea how it works, but they have not really the background, the mechanical information for that. So this is a benefit, an easy example on the ISO standard test, where you can see finite element brings you it's an additional knowledge. Then I come now to the human body model Joe, which I use that. It's presenting a health person. I'm clear, this is not the real patient. I will tell something about that later on. It's a male, 15th percentile. It's based on a CT scan for skeleton, MRIs for the layer setups, body scans for the outer surface. We have some additional information for the tissue. And that's the general setup. And here we see it in interaction with one cushion. So, and what is important when you do that model? The modeling, especially regarding vibrations or seated setup, is we need a very accurate model, yes, of the tissue, but especially we need a very accurate modeling of the lumbar spine, because the lumbar spine is, we have the trunk, we have the head, and all the load typically in a seating process is transferred by the lumbar spine to the pelvis, and the pelvis is finally the supporting part. So I would say it's the main load transfer column what we have. And it's also very flexible, especially the lumbar spine. So we have really to model that in a very specific way. And I will directly show you in 1 or 2 slides why is it also important to have a specific detailed model for the analysis of the dynamic setups. Another point you have to consider is muscles would be nice. If you don't have the muscles, maybe you need some belts to keep you in place. If this is not the case, you should take into account in the modeling some muscles. So this is the model I have only modeled some of the back muscles, some of the abdominal muscles without any activation. And this is just showing the same model with some activation to keep the neural shape we have for the spine, and you can vary that. So this is another point you should normally consider. What you do with this kind of modeling setup, you have to validate it. Obviously, first setup is validation by pressure map. Here, comparison, 9 male test persons in a range of 70.4 plus minus 2.6 kilos. We see the pressure maps, and on the left side, this is the result of Joe. And I would say this is an acceptable result, so we can start using that. We did also do some further quantification validation when we looked on the lumbar spine. There's some data when you do just a segment L4, L5, how much is the deflection. And this also works fine. It shows a good correlation. So coming now maybe to the comment, okay, this is a healthy person. You're right. The difficulty is with our patients in this industry, it's difficult to get data. It's difficult to get the right setups. And then if you model one of the patients, you have only one specific patient. And the goal here for this setup is not really to make an individual setup, but to have some general recommendations if a design works better. Because if I can show for a healthy person that the vibrational level is reduced, I can also say, okay, I assume this is also the case. Maybe not the same amount, but I can say this design is for this setup better. I assume that's also for our patient better. And that's the idea. Hopefully in future, it's getting easier, getting some data of the patients and to develop some patient-specific models. Coming now to the difficult part, and here you can see I'm an engineer. I'm sorry for that, but that's our nature. So equations. I described the whole system, and I said you need the human body on top, because I said the human body has some kind of dynamics. And it's known there's a value which is called the apparent mass. And the apparent mass is a good value describing our reaction to applied body forces. What we here see in this slide is a test rig at the FINITE in Berlin in 2008. And they applied some forces here to a rigid plate. And then they measured, not they applied forces, they applied some accelerations. And then they measured the reaction forces, which are force plate here. And based on that, they defined, normally, you know, all force is equals acceleration times mass. They said, okay, we will convert that to mass is equal force divided by acceleration. And they found out it's very known that individuals of specific percentiles have very similar characteristics. And therefore, it's a good value to define the reaction of a human body which is exposed to accelerations. And this is also value you have to take into account for your human body. You see that this is the right side. This is the apparent mass values of Joe, which correlate well with some results of that study. And here on the left side, when you see here peak, this is a frequency, what means with a specific frequency, the acceleration is applied. This is the main peak, and this is our resonance, our main human body global resonance. And this looks like we see it here on the right. So the acceleration is applied here, and we see the trunk is moving up and down. And the main segment we can see what is doing a lot is the spine. And therefore, it's really important what I said, you need a detailed model of the spine that you can cover that. Because if you would have here a rigid block, you cannot really assume when I put it on top of a wheelchair that I get a realistic result as when a human is really in reality sitting on a wheelchair. So this is a very important part that you should consider that in this kind of analysis. So, but enough of theory, now going to the pilot study. The goal was, okay, let's do a setup which is somehow similar to the measurements of Wolf. And then let's see, use the finite element analysis and see are we in close to the vibrational levels, and then focus more on tissue loads, not on accelerations. The first one was, okay, we have just modeled a manual wheelchair. It's based on a technical drawing, nothing specific, a standard foam, really nothing specific. We said, okay, we are not highlighting here any products. We just want to get knowledge. Okay, what does this work, and what is the benefit for us? So, and then we did, okay, we model a pavement like we seen it here by Wolf. We model a pavement which is somehow typically the stones with the width of 200 mm, length of 100 mm, and then a 6 mm joint. So this is one of the setups. And then we said, okay, let's model as there a length of the pavement of 7.5 meter, and then speed him up. First, let him settle down. For this analysis, we use Abacus explicit. Let him settle down. You see at the beginning, the wheels are a little bit, they need some friction to start. And then we speed him up to 1 meter per second, and then keep the speed constant. And then he's moving over the pavement. Okay, we said, okay, this looks very close to what we see in the measurements of Wolf. Let's have a look what kind of RMS value or the acceleration value we get. The measurements at the Wolf study have been carried out on the frame. So we looked here on the frame. And here you can see on the left side, this is how he's going over the pavement. Here on the bottom, this is the acceleration at the frame. No, this is the acceleration at the buttock. But we looked first on the setup. We got a value of 0.68 meters per second squared. And this is very close to the setup of Wolf, which was 0.59 plus a standard deviation of 0.09. So we are within the standard deviation. So we can say, okay, the model, what we have here virtually with finite element analysis is regarding the vibrational level, very similar to what we have at Wolf. So it's a realistic scenario. The first one is then we said, okay, we will not focus on the frame. We will just look on the buttock and say, okay, we compute as I have shown you by the procedure of the European standard. We put here we don't have to put there. We just look what is the acceleration in this area. So the acceleration is here going over that. And you can see there's some bumping. These are the joints coming here from the pavement. And then we computed an RMS value of the buttocks, which is 0.31 meters per second squared. Okay, fine. This is below our action value. Then we said, okay, now look on the tissue loads. So what we see in this setup, cross section, same animation, he's going over that. And on the right, we see the pressure. The pressure and you can see that it's a little bit oscillating due to the joints, because it's like small bumps, always, again. And you will see that on the pressure map. I would say this is not also a big deal when you do that kind of analysis for measurement, but we did it here because we have been interested. Okay, we are with 0.31, we are below the action value. We don't have to do anything. So what does it mean for the tissue loads? And the question was here, we see there's an oscillation, and when you normally have an oscillation, this means you start from a point and you go up and down and up and down and up and down and up and down. And the question was, okay, when we look on the pressure map, how much we are going up? And this is just comparing here on the left side, the static after we settle down due to gravity. And on the right side, we see, hopefully it's correct. Yeah, I will just show it by the mouse. This is when we have this is the maximum of 6 millimeters joint. And this is after the static loading, just applying gravity. And we see it's an increase from 1.7 to 1.97 newtons per square centimeter. I will just convert it to typical values for you. This is about 150 millimeters of mercury. And this is, let me just count, this is about 130 millimeters of mercury. So it's a difference of about almost 20 millimeters of mercury, which is, I would say, although we have a very low vibrational value, which is an increase of 16%, which is not really less, or not really a small difference. So then we did on top, I said already pressure mapping is no problem. On top, we did some computation of what's going on with the internal tissue. So we have a possibility that we can compute at each setup the tissue load internally. And you can see that this is the settling down process, and we call that, how we compute that, volumetric strain distribution. When I stop that here, so let me just go here. I will stop that finally. So this is after settling down of gravity. So, and then internally for each part of the volume, I can say, okay, you have compressive strain of that amount, you're going to this range, you're going to that, you're going to that. And then I can separate the volume, and we focused here in the IT area. Okay, how much of the volume is in a specific threshold, which is critical? Because there are some critical values. There is some studies of Williker of 2000, let me just see, 2018, that he say, okay, below 50% of strain, no problem. With some tests between 50 and 80%, this could lead to necrosis, but we are sure if you're above 80%, then it directly in a short time, you have some damage, which is not even reversible for the tissue. So this is the point. And what we did for each state, I said, okay, settling down, then we did how much of the volume is between 0 and 10, 10 and 20, 20 and 30, 30 and 40, 40 and 50, 50 and 60, 70 and 80, and above 80. So we compute for each setup how much of the volume of the tissue is in these different strain ranges. And then we can say really a value. And based on that, when we now compare the two designs to each other, we've seen, okay, it's only 60% or 70% of increased pressure peak. But when we look internally, we see, okay, it's much more, especially for the critical range. So what means maybe the pressure setup is not enough information. If we use that, we can really see this is much more critical as the previous setups. And this is a point, okay, helps us getting better understanding of the risk of the vibrational loads. This is just a summary. Yeah. And the comment is we have 0.31, no action, but still we see here a strong increase. So what does it mean? Is it not covering the risk? Should we do something? And this is a point where we say, where I would say, okay, we need some deeper insights and we can then make a decision, okay, let's look on the design and let's improve. But this was only the first part. We have been then interesting, okay, when we changed the variation. We did 3 additional cases. We put some cobblestones. Maybe you remember we had this, I would say, loose pavement with a PRI value of 70, 47. We did just say, okay, a little bit of loose. So what means some of the cobblestones you see there have a height increase of 1 or 3 millimeters. The one is the orange and the dark one is 3. Then more loose cobblestones, we increased the height increase from 3 to 5 mm. And finally, we put some obstacles. You can see that here in detail, our obstacle which is going 50 millimeters up and another obstacle which is going 50 millimeters down. So this was maybe the example of the pavement we have seen in the middle of the previous slide. And here this shows now, once again, a cross section. Cobblestones have been not so nice to visualize. I was focusing on the obstacle. Once again, now the obstacle come, you go over it and you see what happens to the pressure map. I think this is not, yeah, it's maybe interesting. We assume that. We also see that here the obstacle going up has a much higher influence than just going down. I will just repeat it. Oops. Sorry. So he's turning the wheel to get the right speed, to get the right friction with the pavement. And then very, very fast now the obstacle comes. The front wheel is going up. We already see this is an influence, but then second point, he's really just bumping out of the seat, and you can see a strong increase of that. And the question was, okay, what does it mean for our values? First, we just did it as before, RMS. This is just showing us the buttock value, and for all 4 variants. The dark blue, you can almost see it's almost close to the, as a relation of 0, is the initial setup with a joint of 6 millimeters. Then already the green and the blue ones, these are with the cobblestones with a different height of 1 and 3 and 5 millimeter. And then you see the obstacle. The obstacle is directly here. You can directly see it. At the beginning, nothing happens, and then the obstacle comes, and it's really so. And the question is, what's going on with the RMS value? And then we looked on that, and directly we see, okay, if this would be the case, yeah, this would be really a strong increase. And normally you directly could say, okay, this would help us using here the typical standard is we directly can say, okay, we need some action here. In this case, also, it's not allowed. You have to do something against it. But the question, could we really prevent that with the stand measures? Can we say, okay, you are not allowed to put an obstacle of 15 millimeters on a pavement? But the other question is, can we not just use that information and do something? But in my opinion, when we talk about this topic with the manufacturers, with the users, they're not really aware because they cannot transfer this information to typical risk values. This is something I mentioned before. And so I'm coming back to pressure maps. Pressure maps here showing for the 5 setups: static seating, 6 millimeters of joint, up 1.3, up 3.5, and obstacle. And directly you can see what you imagined. Okay, slight increase, strong increase, very strong increase, but only one peak. And then we converted that to a pressure value. We had seen before, once before, the previous relation was just computed with 100% static. Now we said, okay, we want to use a dynamic setup with the 6 millimeters, 100%. And then let's see how much is the pressure maximum increasing. And we see the obstacle is about 80% increasing. So this is a really strong value. And maybe people already say, okay, this is also a strong value, but we not really understand it. But if I would tell you, okay, here we have about 150 millimeters of mercury and 80% on top, let me just count, this is 270 millimeters of mercury. Then people directly will say, okay, we have to do something. Can we reduce that? How can we reduce that? Is it what happens if we use a different cushion? What happens if we use air tires? What happens if we have a suspension? So these are possibilities. People understand that. And to make it more clear, I just computed there also the compressive strain with the VSD plot. You see 60 and 70% is not really something happening. But then just look on this where I said, okay, typically is this the case in a short period? So you don't have to have that 1 hour. In a short period, then you have a risk of cells necrosis. And we look here, initial, not really, this is, I would say, a numerical effect, but we see already 6 millimeters increasing, but we see especially for the obstacle, the max increasing setup, this is very critical. And this is the point where I said, okay, let's discuss that, see what we can do here, how we can improve our setups based on that. So here, once again, the numbers, you see, this is a very small number. When you do this kind of finite element analysis, you can say, okay, not really take that into account. We have to focus on bigger numbers because we have some tolerances there. But when we compare 6 millimeters with the obstacle, it's always a factor of increase 120%. And this is really something very critical. We have to think about what we can do just to get an understanding that this is a risk for the patient. This is a risk for pressure setups. This is just to get to the community, the understanding vibrations is on top of a standard procedure is an additional risk. And we should at least be aware of that. And if we have some possibilities to work on that, then we should do that. Because imagine, I said, you have tires, you have frame, you have cushion. Mainly we are working on cushion, say, okay, we have a big difference. But let's assume we have for both cushions this kind of increase, which is not the case. And let's assume I can use air tires instead of rubber tires. The question is, what is more effective vibrations? Is it change of cushions or is it tires? And are we playing too much in cushions and not considering tires? Would it be not better to have tires and cushion optimized or frame tires and cushion optimized? So this is the question I come here. So, and I'm close now to the 45 minutes. So I would say I'm just in time. because then I have 1 minute for the summary. Just summary what I have shown to you. In this pilot study, different setups for vibrational loads of wheelchair users are investigated using the FEA approach and using our virtual human Joe. Based on the results, it could be shown that the RMS values, so the acceleration values normally used in the evaluation of the human body following the European standard, are at higher intensities, which is a first indicator for the pressure injury risk, which also was the case in the studies of Wolf and all the work done by the University of Pittsburgh. For lower arm values, the risk of pressure injury seems to be a little bit underestimated. We have seen, although we had only RMS value of 0.3, we see an increase going over the 6 millimeter joint pain at about of 20%. Nevertheless, a detailed evaluation of tissue strength is more accurate, or gives you, I would not really say more accurate, it's just giving you a better understanding, more information. And based on known threshold values, which are already defined and which are somehow practiced in the wheelchair industry when we look on developments of cushions. And finally, this was only a pilot study. So wheelchair design factors like tires, suspensions, and cushions should be evaluated using the simulation process. I know there have been ongoing work or presented published work on cushions itself, but I think there's a little bit more potential to have some further knowledge which could be helpful. And the main part I want just to distribute is here, get an idea how vibrational loads influence the tissue loading, and get an understanding, okay, this is not something I don't have to care. It's really something you should care. And this was my final message. I thank you for your attention, and I'm happy to answer your questions.
Thank you, Alex. I encourage people to put questions into the chat. And while they're doing that, I guess I'll kick it off. Right now, there are no questions or comments. One thing I thought about, Alex, as you were presenting was, these are somewhat like impact loads. And there is actually some standardized testing for cushions that look at impact damping of cushions. And I guess it's more of a comment, but it could be a question. It's like, do you see value and possibly some correlations, looking at associations with that impact damping capabilities of cushions?
I would say, yes, obviously there's some relations. I'm not familiar totally with the standards specified for that, but I would assume that these standards, are they more or less on crash situations when you define impact, or are they on lower obstacles? Because 15 millimeters is not really a big obstacle. And you are right when we look here on the change of the obstacle and of the influence here. But when we look, for example, on the result of a 6 millimeter joint, this is not an obstacle. This is a lower intensity of vibration. You would not really recognize that. And therefore, I would say, I agree when we look on the obstacle, and maybe there could be some information which is already there by the test setups. But I would not really agree when I look on typical lower level of vibrations.
Mm-hmm. All right, makes sense. Okay, we do have a question in the chat. Is a modeling service available, for example, testing different wheels, such as loop wheels?
Yes, it's available. But we have not carried out that. So here was just to give an idea what is possible, to give people an understanding what is there any relation? Because I was once at a conference and see really on booths, okay, we can reduce our amplitude using that kind of system by a factor of 2. And then I asked, okay, what does it mean in pressure? And this is the point I want to make. It would be interesting really to have some studies with manufacturers, and we are open, we provide this kind of services to say, okay, this is the benefit if you use that system, or what can we do to improve that? Yes, services are available, and this would be one of the next points we want to do.
Great. Okay, we do have another question. Would you expect to see any differences between body types, muscles, and species? Example given, the strain data from the 2018 paper by Uman's group was based on the anterior tibialis of rats.
Yes, I would assume that. I would assume that because when I would show you the apparent mass already, there you see a difference between small woman, mid-sized woman, big mid-sized man, and big-sized man, which are the typical categories when you do this kind of transmissibility analysis in cars. It would not change the tendency, in my opinion, but it would obviously change the level. Okay, and the question is that, okay, is it necessary for all setups? Yes, I agree. This will have an influence. Future work. I'm sorry. I hope this answers the question.
Okay. We got our 10 minutes heads up. Next question is, can you share your contact information? No, it's a comment, I guess. Please share.
Yes.
To do that. And then there's another question that came in. While you're doing that, do you think modeling provides more value for monitoring vibration dosage, etc., pertaining to wheelchair suspension, such as coil over oil damped shock absorption?
I just got.
Go ahead.
Can I see the question also in my chat?
Yeah, you should be able to. It might be easier to read.
Yeah, that's because it was dosage. If you understand it like I do, I will just explain that. Typically, when we look on, as Patricia mentioned, talking a little bit about impact, then typically impacts are counted different in the RMS value than lower level of intensities. It depends a little bit what kind of impact you have, and you call normally dosage. It means it's a higher level of. So here we have root mean square. It's a higher level of potential you take into account because it's assumed that the impact, you cannot just count it like a lot. So what means one strong impact is not if you just count a lot of numbers, smaller vibrations. You get a higher, level of that. So let me see. Do you think modeling provides more value for monitor vibration, etc., pertaining to wheelchair suspension, such as coil over oil damped shocked, or would doing something such as mounting SMS to different portions of the chair provide better data? Is the question related to modeling or measuring? Oil damped shocks. I would say modeling on typical vibrational levels, lower levels, is a little bit easier. Typically impacts covering also here some fluids is a little bit more difficult to investigate. So I would first start to look over the whole setup of the frame, what are at the different locations, and of the setup, and measure that before I directly would go for the shock absorbers. I hope this answers the question. If not, please contact me afterwards. You see here my email address. I'm open to calls anytime. Only consider that I'm in Germany, so I'm 6 hours before. So don't give me a call in the night. Then Patricia, next question, or
yes, next question. Yep. How would lowering the air pressure in pneumatic tires affect this scenario, though possibly making it slightly more difficult to propel?
Yes. So I have not investigated it in detail. So this is something off the records, I would assume. Getting a little bit closer to the detail. If I would have a very high internal pressure of an air tire, then it has a high stiffness and it's not allowed to take over any movement. Okay, therefore I assume higher pressure is normally higher stiffness is not reducing the damping. I would say obviously reducing the air pressures in the pneumatic tires would reduce the vibrational level because the tire itself can a little bit deform. And I would say yes, in general, but it could be that on a specific point that then, for example, the tire needs movement. And if he loses that and he gets a rigid contact, you have to prevent that. So you need still of movement, and you need a little bit also to investigate what is the outer part of the tire, how is what is the wheel made of. So in general, I would agree. Yes, it will reduce the vibrations. I think this is more or less known, and but I cannot really say this is the best, because it's a combination of size of the tires and the construction of the tires. I hope this answers the question.
I think that addressed it pretty well, and it's you have the ability to do parametric studies and vary these things.
Yes.
And that's what's really of great interest and value of the work. Any other questions or comments? One thought I had, I'll throw in while we're waiting to see if there's any more, is that time, in addition to the stresses and strains on the tissue, is a factor.
Yes.
You know, so, and how does your model consider, you know, time?
Are you talking about viscoelastic effects of the tissue, or are you talking about that the duration? How long?
Duration of stress and strain on the tissue, and the time factor associated with necrosis.
Mm-hmm. It's 3 points. First one is when you settle down, our tissue will not stay the same without necrosis. We have some viscoelastic properties. Normally it takes a while and it has some viscoelastic properties. This is somehow taken into account. Second point, if you say, will we really cover the whole long-term range? No, this is not covered. And the third point, if you're really talking about necrosis, means tissue will, we know that from studies of women's given, tissue will change when a necrosis starts. There's a little bit of discussion. Is it stiffening and is it reversible? So this would you have to include a damage model into the setup, taking into account how long is the load strained and what happens to the tissue. I have supported a master thesis in my previous company. We included that, but in this model, it's not the case. So it's general, but you need more information. And then you can take that into account, if this answers your question.
It does. It does. And I know there can be instant mechanical damage to the cells, right? And then there's also the damage that occurs over time.
Yes. And you have just to find out the values.
Right. Okay. There's 3 minutes left. There's no additional questions that have come in. I posted the CEU code into the chat. You could still post a question if you'd like to, but I'll just state the CEU code is TK6GGS. TK6GGS. And otherwise, also, Alex, you've gotten some thank yous for a wonderful presentation, and we do appreciate the work you do and the information.
And can I make a final comment? Just a little bit of promotion. I will have another presentation with Bart van der Heyden at, let me just see, your time PM, giving you more information using FEA for seating intervention. So when this is interesting, this could be also interesting for you. Sorry, a little bit of advertising for us.
All right, more information.
Okay.
Okay, all right.
And I thank you.
Thanks, everyone.
Thank
you, Alex.
Have a lot of fun with the conference, and thank you all for enabling this. Thank you. Thanks, Patricia.
Thank you.
Okay.